So what we can do here is what's called to see it even better, we can do what's called a change of variables. Also commonly known as u-Substitution. For whatever reason, u is the variable, but it could be v substitution or w substitution or b substitution. Doesn't matter. So what are we gonna substitute? We're gonna say let u equal, if u is e to the x, then what would we have here? So then if u is e to the x, then we'd have u squared over u squared plus 3u plus 2. All right, so now, but it's not just necessarily du for dx. So we got to figure out what dx is. So if u equals e to the x, then du equals e to the x dx. Little chain rule there. So so du doesn't equal dx, right? Dx doesn't equal du. What does dx equal? Dx equals du divided by, and what's e to the x? So dx doesn't equal du. It equals du divided by u. Do you see that? If u equals e to the x, then du equals e to the x dx. Solving for dx, we get du over e to the x, but e to the x was what we called u. So we can't just, when we change variables, we can't, sometimes we can, but we can't just take it for granted that dx is du. It's not in this case and in many cases, so we need du over u. And so then we've got a u squared in the top and a u in the bottom, so that leaves us with u over u squared plus 3u. So we've just changed the variable of our original integral. This integral right here is equivalent to this one if u equals e to the x. So these are equivalent integrals if u equals e to the x. How are we going to do this one then? U over u squared plus 3u plus 2. Okay, so these are all u's, by the way, no a's. So the denominator factors, and we can use what technique? Partial fractions. Okay, partial fractions. So we can say this is equivalent to a over u plus 2 plus b over u plus 1 and this is a super easy one, much like your quiz, so I'm just going to write down the answer. A is 2. And b is negative 1. So normally, so if you don't know that by looking at it, then you're like everybody else. You're like most, and that's fine. So I'm skipping all the work, right? I'm skipping all the work of solving for A and B because we've already done that. You guys just showed me you could do it on the quiz. And so then this result is what? 2 natural log minus C. But we were solving the antiderivative of the original integral, which was an x integral. So our final answer has to be in terms of x. So we use this change of variables to make life easier and up until taking the antiderivative, and then once we have the antiderivative, we're going to switch it back to the old variable because we're really solving this problem, right? We're not solving a problem. We're not really solving the problem in terms of u. We're solving it in terms of x. So how do we switch it back? What does this equal? Equals to natural log of e to the x plus 2 minus so just make sure you know that there's a mess of work in between there that I didn't show, okay? Just because I want to focus on the idea of the changing the variables, u-Substitution. By changing it into this other variable u, by letting u be e to the x, then we clearly see that it's just a partial fractions problem. Whereas it's a little, you know, it's 1 degree more complicated when the e to the x is in there. So by making u e to the x, it kind of takes that element of complication out and lets us just freely look at the partial fractions without the distraction of the e to the x, and then we can just substitute back at the end. Questions on that? Does it make sense? Yeah?
Right in the beginning when you took the e2x and then you called it e to the x squared, because we have power raised to a power, you just multiply it out. Is that how that works? The very first change that you
Yeah, so if we think about, say, you know, 2 to the 15th. So what is 2 to the 15th? So you could think of 2 to the 15th as, that's 15 2's multiplied together, right? Fifteen 2's, right? Multiplied together. So what is 2 cubed? No, but what does it mean? 3 2's multiplied together. So if I did that 5 times, so if I multiplied that together 5 times, how many 2's would I have? Right, so if I took that 3 2's 5 times, that'd be 15 2's. So that's the same as 2 cubed to the 5th. Other questions? Okay, so let's look at another example. How about okay, what about this one? First question we ask? We go and do the chain rule. No way, right? No way. So, and and actually there's really there's no quick change we could make, like one simple change to make it undoing the chain rule, right? This is just. What about other techniques? What about undoing the product rule? Maybe, but this is squared, and this is then you have something to the -1/2. So it's not one of our common forms for undoing the product rule, right? What are our common forms? Like x times sine, or x times e to the x, or something times natural log of x, or just natural log of x. Those are the basic ones. So maybe we could do undoing the product rule, but it might get a little hairy, okay? So we could work on it, but it's not going to be a simple version or simple example of that. So what substitution could we make that might make our life, that might make this a manageable integral? Yeah, that's what I'm saying. What do we let u equal that might make this easier for us? Okay. Yeah, right. Yeah, exactly. So let's do the inside of the denominator. So we've got u equals, so that takes care of the denominator in terms of changing this into u. So we've got a couple things left to do. We got to figure out what x is in terms of u, so we can get that x in terms of u, and we got to figure out what dx is. So if we figure out what x is first, then dx will be one step away from that. So how do we figure out what x is in terms of u? And what are you doing, Ruth, when you do?
I don't know how to say it in English. You just switch the numbers to the other side.
Yeah, you're solving for x, right? You're going to solve this for x. So when you solve this for x, what happens? U minus 1 equals? So x is 2 times. So can we just do 2u minus 2? So that's going to go, that is x, so we can put that there. Last thing we need to do is get dx. What is dx? 2 du. Now we've got everything we need. We know what 1/2 x plus 1 is, we know what x is, and we know what dx is. So rewrite the integral in terms of u. Go. You rewrite that whole integral so it's all now in terms of u. So what's in the parentheses then? He wants 2u minus 3. Agree with that? Exactly, because it'd be 2u minus 2, then minus 1. So we can that just becomes 2u minus 3. Okay, well, did it help? It definitely helped if you know what to do. If you know how to proceed from here. So we can just take let's take the 2 out. How do we proceed from here so we have something? So is this undoing the chain rule? No, right? It's not. What can we do to make this something we can find? What's that? Tell me. What would it be? Okay. Minus 6, but there'll be 2 of those, right? Okay. All over. Why is this helping? Can we now do? Right. So now remember this technique we talked about that's shown up multiple times? That is splitting a fraction up into multiple fractions. So what's the first one? 4u to the what? 3/2 minus 12u to the 1/2 plus Did you catch it? See what happened? This would have never been possible leaving it in terms of x. Right? By switching it to u, getting just the square root of u in the denominator, we can multiply out the numerator, and then we can combine, make it 3 fractions, and use power rules to just get basically just individual terms that are easy. Okay, so we got, what is this going to be? 8 times 2/5. Should we just keep the 2 out? So 4 times 2/5. Is that 10/5? X to the 5/2 minus 12 times 2/3. Is that 8? And then it's going to be 1/2, so 2, 18. So it's just, we can just use the power rule 3 times, right? We use the power rule 3 times, get our coefficients right.
First one should
Why
be
is that?
Yeah, it should probably be something else. 5/2. 2/5. 8/5 instead of 10/5. 2/5. 8/5. No, but I just kept the 2 out. Just keeping the 2 out of the whole thing. So it should be 8. Yes, because 5/2 times 8/5 is 4.
and that should be u, not x.
Yeah, that should be you. Thank you. Now that we've taken the antiderivative, now we want to get this in terms of x, right? So what does it equal? So now let's distribute the 2, okay? Or should we factor out? Let's distribute. Just keep them separate terms. So 16/5 instead of u to the 5/2, it is 1/2 x plus 1 to the 5/2. Minus 16, 1/2 x, 1 to the 3/2, plus 36. Let's see. So look at this original integral in terms of x, and look at our answer. So you see that we'd have no way to do this without that change of variables, right? So it would be totally unclear how these three terms made up the antiderivative of that, right? But the key was that change of variables that we were able to do, multiply out that top and get three different monomials. We could just use simple power rule on each one. Okay, so now suppose that this was a definite integral. So let's think about a definite integral. Suppose this was the integral from 7 to 10. Okay? So two ways to think about this. We could, so what kind of values are these then? 7 is what kind of value? It's the value of x, right? What do we say? This is the total change as what? X changes from 7 to 10 when the rate of change is this ratio, right? That whole thing is the total change in some quantity whose rate is this as x changes from 7 to 10. So we could simply just come here to our answer in terms of x and just evaluate from 7 to 10, right? That's no different than anything we've ever done. It still works, right? We've got our antiderivative in terms of x, plug in 10, plug in 7, subtract. But then there's kind of a different option for this now if you have a definite integral, and that would be, yeah, so let's get this definite, we have this definite integral in terms of u. Does u go from 7 to 10? What does u do? So when x is 7, u is 9/2. Is that right? And when x is 10, u is 6. So rather than switching, if it's a definite integral, rather than switching back, rather than switching back into x, we could have just taken this one in terms of u and integrated from 6 to 9/2. And that amount of change would be we'll get the same amount of change by doing 9/2 and then 6 and subtracting.
9/2 to 6.
Other way around? Thanks. So when you have a definite integral, you got two choices. You can switch back to the original variable and use the original limits, or you can switch the limits into your new variable and then just evaluate your first antiderivative in the new variable with the new limits. Does this make sense?
Yeah.
Any questions on this example? Okay, you guys tried this one. Okay, first question. How could you change this? How could you make one small change to this so that undoing the chain rule would apply? So everyone answer that, and then evaluate this. Evaluate this, not the altered one, right? So what small change could you make so you could do undoing the chain rule? But then evaluate this one that I'm giving you.
Is that x cubed or is that the cube?
No, it's the cube root. Whoa. Okay, confirm. Make sure you confirm with somebody. Or if you've got a question, ask. You guys all have the same thing? You too? Confirm it. Check with, if you're done, check with the person next to you. Okay, here's what you should have got. Is that yes? Is that what you did? Yes, yes, yes. Okay, and so then this is u to the 1/3. So basically we have u to the 4/3 plus 2u to the home free, right? So this is u to the 3/7 plus, let's do 2 times 3/4, is that right? U to the 4/3. And then our u is x minus 2. If we had limits of integration, we could switch back to x, use the original limits, or we could subtract 2 from both limits and use this, right? Because the new limits for u would just be 2 less than the old limits for x, according to u equals x minus 2. We have. Is that what you got? Some nods, thumbs up. Joseph, you good?
I'm good.
Adrian, Daphne, you guys good? Okay. So then this technique is really helpful for some more complicated integrals in which we're going to use tables in the back of the book. So let's look at one of those. Okay, so here's an integral. Definitely not undoing the chain. Certainly not one of the basic forms for undoing the product rule. Okay, definitely not partial fractions. So then we think, okay, u-substitution. If I let u equal 4x squared minus 7, then it's not really going to help because I'm gonna have something I'm gonna end up with something complicated of u here in x squared, and that so just doing u equals 4x squared minus 7 isn't going to make this easier necessarily. So here's where tables comes in. Okay, so tables we have just there's dozens and dozens here. It's up to 106. There's 106 common forms of integrals where they just give you the antiderivative in the table. Okay, so we would come, and they're grouped by different types. So they have basic integrals. We shouldn't even need the table for that. And there's trigonometric integrals. Reduction formulas. Well, that's what we just learned with the trig. But then there's these, starting with number 61. It says, I wish I had there's no dot cam in here. I could show you, but so 61 through 66 in the table. They're numbered. Each formula is numbered. 61 through 66 are integrals involving a squared minus x squared, where this is like a constant. Okay, is that what we have? No, we have something more like x squared minus a squared. Well, that's 68 through 75. So 68 in the table, 68 through 75 are integrals involving x squared minus a squared. That's what we have. We have something like that, right? We have something like our argument squared minus, now 7 is just, we could make that what square root of 7 squared, right? So that's like, we can say that that's a constant squared. So this is where we're going to look. And so then if you look through that list, then you see that number 70 is this right here. It says the integral of dx over, so what I'm going to do is this is a little confusing because they're doing it in terms of x, so that's a little bit confusing. So I'm going to change it to du. Okay, so 70 looks like this. Du over u squared, square root of u squared a squared. And you see that's pretty dang close to what we have. It follows that same pattern. Okay? And then they just give us that antiderivative. It's going to be natural log of u plus square root of u squared minus a squared minus square root of u squared minus a squared over u Let's see. So the table is a bunch of general forms with the answers, with the antiderivatives. So what's our work then? Our work is we got to get r's into that form. We got to get r's to look like that form so that we can apply the formula, because we're not ready to do that yet. It's not exactly the same. What's different about it? Yeah, ours is 4x squared when this needs to be strictly u squared. So that's gonna dictate how we do the substitution. We need this whole thing to be u squared. So we need that to be u squared. Therefore, what is u going to be? So u needs to be 2x. Do you see that? If u squared equals 4x squared, then the u that we need is 2x. Okay, so we got a couple other things to take care of here. What is a? So this is then this 7 is our a squared, right? So what is a? Radical 7. But if you notice in the answer here, the answer always has a squared. So it's just gonna be minus 7 and minus 7. Okay, so we could say yeah, a is radical 7, but we don't ever need that, because when we come to the step of using the formula, we're just gonna have minus 7 minus 7. Do you see that? Okay. So now we need to get what x squared is, and we need dx. All right. So what is x squared? We look. X squared is going to be u squared over 4, and what is dx going to be? So x is 1/2 u. So dx is 1/2 du. So this is our setup work. This is our setup work to switch this thing to make it look like this, the table formula. We gotta have it look just like this so that we can apply the formula. All right, so then what is it? So we got square root, or integral of 1 over, so what is x squared again? X squared is u squared over 4. 4x squared is? That's what we wanted. And then we can just keep it as minus 7. That's fine. We know that that's a squared, right? We know that's a squared. And then dx is 1/2 du. So we're one step away. It has to look exactly like this in order for us to apply the formula. So what do we have? We have a 1/2. We're going to pull it out. But 1 over 4 in the denominator. So that's just really like multiplying by 4, right? Okay, let me know if I lose you. So by doing a u substitution, forcing that 4x squared to be u squared, like in the formula, and then following where that takes us, right? U squared equals 4x squared takes us to x squared being u squared over 4, and dx being 1/2 du. Get those constants out. That's really multiplying by 4. That's times 1/2. Get those out of there. And now notice this is exactly like the table now. So now we just write down the answer, right? So it's going to be this just amounts to 2. So it's going to be 2 times this whole thing, right? Because we know for this, here's the antiderivative. This is going to be 2 natural log u plus oh, so our a squared is what? 7. So our last step now is to change it back into x. Right? So all we need to know is what u is and what u squared is, and we got it. So 2 natural log of, what is u? 2x, right? 2x plus square root of 4x squared minus 7 minus 2, I distributed the 2, 4x squared minus 7 over 2x plus c. So there's this, the table in the back of the book is there by number. So we, for this particular problem, we use table entry 70, telling us if you have an integral that looks like this, that's the antiderivative. So we noticed that we could make ours look like that with a u-substitution. Then once we get it looking exactly like that, we just write it down and we substitute back in. Anybody have questions? Yes, please. No, of course not. The whole point is no. The whole point is that you have the table. If you're using a table, you use the table. Yeah.
So for the test, you'll give us like.
Yeah, exactly. So if there's a table integral problem on the test, I would give you like maybe 1 page of ones, and you have to figure out which one to use, and then figure out how to get it set up to be able to use it. Other questions on that? Okay, so we kind of saw different applications of this u-substitution. One, the first case was it took away a degree of complication, so we could just get rid of the e to the x and see that it was basically a rational function for partial fractions. The next two that we did were, it like kind of required doing that substitution so that we could do algebra to get it something we could do. And here we see u-substitution coming in to enabling us to use the table formulas. Okay, questions on that? You guys look like maybe this is kind of dry or something. I agree, it is. So, you want to meet my kids? Okay, there we go. Those are my kids. So maybe another day we'll have a more flattering video of my son. Okay.
Did you try making him integrate?
No, we're still working on just a few words. Okay, so let's change the subject here. We want to do something now called improper integrals. So we've basically made it through all the techniques, right? Undoing chain, undoing product, partial fractions, trig integrals, and u-substitution, and then tables. So kind of new subject here, changing subjects, improper integrals. So consider a rate of change function that is always positive. For example, a population that grows by, say, 2,000 people per year. Maybe this is a city, okay? What is the long-term result to the quantity, in this case the population? What will happen if the population has this rate indefinitely? So thinking long-term result. So let time just increase indefinitely. What will happen to the quantity, to the population?
It become infinite?
So two of the guys are saying it'll become infinite. Agree?
Is this assuming nobody will die?
The population, it's growing by 2,000 people per year. That's the net effect of everything. So what do you think? Go to infinity. What does 2,000 people per year mean?
Every year, change in time, the change in people is 2,000 more than the change in time.
Right. Okay. So given a change every year that goes by, 2,000 more people in the population. So if you let time go by indefinitely, it's just going to keep growing by 2,000 every year, right? So the population will grow infinitely large because 2,000 is added every year for an ongoing number of years, right? So there will be no limit to how big the population gets. So what am I showing you here? What is this showing? This graph? It's the rate of change graph, right? Rate of change stays at 2,000 people per year. But I thought you said it was growing infinitely large. Right, that's not the quantity, that's the rate of change, right? So this might be the quantity function, maybe starting at something like 3,000 people. That's what that shows, doesn't matter. But now this is showing the quantity, right? This is showing the quantity increasing at a steady rate, 2,000 people per year, according to this rate function. Okay, so what about this rate function? What about a rate function? So as x increases indefinitely, would you agree that this function is always positive? This rate is always positive? Yeah. So as x increases indefinitely, we always have a positive rate. So what will happen to the quantity over time?
Slight increase, but will start to be kind of constant.
It will reach infinity. Infinity x.
You guys are saying, people are saying different things. Some people are, so will it go to infinity? Become infinitely large? We got to, the rate is always positive as x increases indefinitely. So if the rate is always positive, do we conclude that then the quantity will just grow indefinitely large?
No.
Some are saying yes, some are saying no.
No, because x is going to infinity, the number will just become a zero. Might as well become zero. The rate will just, because it will be infinitely small. Yeah, it won't hit zero. It'll come
What's it?
the population. The rate of change, well, okay, yeah, the rate of change will never get zero. This will become infinitely smaller, until it will never reach it.
Okay. So the rate is doing what? The rate is a decreasing rate, but it always stays positive. So if the rate is positive, the population is increasing. So would you agree the population is always increasing? So the question is will it be infinite or not?
It'll always, it'll continue to increase, but at a smaller portion, like, 1/2.
Okay. All right. So let's do the math and show what the result is. So it's kind of like some of us are saying, oh, it's going to, because it's a positive rate, it's going to grow infinitely large, the population. Others are saying, oh no, because the rate is decreasing, that population won't grow infinitely large. So let's do the math. So what are we asking? So what mathematical, is there an expression, a mathematical expression that we can come up with that would represent that question that I'm asking? What would the population be if x is allowed to increase indefinitely? If this is the rate function. You want to do what? Okay, integral of this? How about 1? Is that okay? 0 is problematic, right? Because what is the rate at 0? Undefined, right? So can I go from 1 to infinity? Will this be the same question? So really we're asking, is this infinity? Or is this just a finite number? Does it actually reach a finite population, or does it just increase indefinitely? That's the question we're asking. So yeah. Oh. Okay. So now here's what we're gonna do. You can't plug in infinity. Okay? You can't plug infinity into things, right? So what we have to do is we have to take the limit as a gets really big. So we look at when a gets really, really large and we say, what would it be if a could get to infinity? What would it be? So as a gets really, really large, and then we'll say the integral from 1 to a. And we can plug in a. We can plug in a and then see what happens when a gets really large. We can't plug in infinity. So that's why we write it this way. Okay. Antiderivative. What's the antiderivative of 1 over x cubed? So this is x to the minus 3, basically. So, okay, good. I'll sing it. So negative 1/2 x to the minus 2, or negative 1 over 2x squared. Is that right? And then we're going to evaluate that from 1 to a. So it's going to be the limit as a gets really big of negative 1 over 2 a squared plus 1/2. Did I plug things in correctly? Okay, so now we can evaluate this limit. As a gets very, very large, what happens to negative 1 over 2a squared? She said 0. Agree with that? Is this essentially 0 as a gets very, very, very large? Yep. And so, the value of the definite integral is? Okay, but some of you anticipated this. This was really good. So just because the rate is positive doesn't mean the quantity will whirl off to infinity. So what is required? So what is required? That rate does what? That rate gets, you recognize that your rate is positive but getting really small, essentially 0, right? Essentially 0. And because that's true, because the rate, so let's graph this and see. Oh, I didn't want to do that. No, I can't go back. Sorry. But she probably has it in her notes. You have it, right, Ruth? Okay, so let's graph y equals, what was it, 1 over x cubed? And then we want to graph in a separate pane integral from 1 to one over t cubed dt. So what am I doing here? So first of all, the prime is not derivative. It has nothing to do with derivative. It's just this software. Or you guys, most of you know a graphing calculator, but this software, this just means open up a second graph window. If you use the apostrophe means second graph window. So I'm going to graph the graph of y equals 1 to x of that rate function. And so what will I see? What am I going to see? So let's turn that off. We'll just graph the first one. And we just want to do that x greater than 1. That's pretty good. Okay, so here's that rate function, right? Starting at 1. Here's that rate, always positive but decreasing to 0. So now for the accumulation function, integral from 1 to any value, what will that accumulation function look like? Okay, what's that? Draw it with your finger. Everyone, draw it with your finger. Right. And what will this eventually reach or get really close to? You see this is 1/2 right here. So if I zoom out, I'm zooming out on the x-axis. You see that when x gets really large, it just gets closer and closer and closer to 1/2. Why? Because the rate is getting so small or so close to 0 that it's essentially 0 and you stop adding. When x gets large enough, your rate is so tiny that it's essentially a rate of 0 in the end. Make sense what you're looking at? Okay, so then what about this? What if our rate function is one over x? What about if that's a rate function, what about our quantity? If we let x go on indefinitely, what about our quantity? What do you think? What's that? Same thing. The quantity will always increase but level off. Okay, prove it. Prove it. Can you prove it? Okay, what happened?
I don't know if I did it right, but I got an infinity.
Infinity. Did you get infinity? But I thought this rate goes to 0, so it's going to eventually get to 0 and be really small, and so then it will level out. You guys must have done the math wrong. 1 to a, limit as a goes to infinity. 1 over x dx. What's the antiderivative? Natural log of 1 to a. So natural log of a is always positive, so we don't need the absolute value. Minus ln of 1, which is? That's 0. So what does natural log do when a gets really large? Remember what the natural log graph looks like? And does it level off? Or does it just keep getting larger? Natural log just keeps getting bigger and bigger and bigger. Let's show it. Okay, so the 1 over x cubed rate is blue. Let's do red. Is blue. The new one is red. Okay? And so now let's do the integral also. So the red now is what? 1 over our rate graph is 1 over x. And the red one over here is the corresponding quantity. And does it agree with the math we did? Is that going to level off? So if I zoom out on the x-axis, is it going to level off or not? See this? Just keeps growing. Now this is some weird thing happening. I don't know what's going on with that. That's not right. I don't know why that's increasing, but so yeah, so it doesn't level off. It just gets greater and greater. So what's going on? I thought if the rate goes to 0 and does this go to 0? Does this rate get really, really small? If x gets large, does it get really, really small? Like essentially 0? Yeah. You know, a trillion, a quadrillion, a quintillion. This is essentially 0. This rate is essentially 0. So then why is that quantity not leveling off to a certain finite value? Why is it whirling off to infinity? So the picture here tells 1,000 words. The difference between the red rate graph and the blue rate graph. What's going on here?
Decreases at a slower pace.
What's that?
Decreases at a slower pace.
You said it decreases at a slower pace. What were we going to say?
Were you asking what happens to the rate?
Why does this rate result in the quantity getting infinitely large? That we saw, right? That's what the math shows, and that's what that red graph shows. But then this rate that also gets close to 0 results in a quantity that levels off and doesn't get infinitely large. Why is that?
Because the minus natural log 1 is just 0. No matter how small that rate is, it's still positive. So it's still it's still increasing. Like it's still, population's still growing.
Okay.
Even at a just very small rate.
Okay.
Is it because, like, for the second one, like ln is like an exponential
So you guys are both kind of arguing just kind of about what happened when we did the symbols. And I'm kind of asking more conceptually, what's going on conceptually that results in one. They're both both rates are getting small, as small as you want. Why does one resulting quantity level off and another one get infinitely large? You're on the right track, but they will both get as close as you want to 0. Just make x large enough. But that's the right idea.
Well, then it's just, it takes a lot of time for ln x to get very, very close to 0.
Right, not ln. So these don't have anything to do with it.
1 over x.
Right, exactly. So that's exactly what it is. 1 over x cubed as a rate. As x increases, how does it go to 0? Really quickly. Like, you know, by the time we get to 8, we can't even see anymore that it's not 0. How does 1 over x go to 0 as x increases? A lot slower, right? It hovers higher. And it takes a lot more change in x to get down and get small, and that's why. So, in order for, here's the big punchline, in order for a quantity to level off, you know, as x goes to infinity, as x gets really, really big, it's necessary that the rate goes to 0. It's got to do that. But then that's not enough. It's also got to get to 0 fast enough. That's what this does. 1 over x cubed, it goes to 0, and it gets there fast enough for that quantity to level off. 1 over x as a rate, yeah, it goes to 0. That requirement is met, but it doesn't get down low enough, fast enough for the quantity to level off. It's just yeah, comparatively it's too high, that the rate stays high. Even though it's going to 0, it stays too high, and the quantity just increases indefinitely. Okay, does it make sense? Any questions?
It does, but the confusing thing
Yeah.
for me is that eventually we get as close to 0 as the other function.
That's right.
So I know that it's just a matter of how fast it
Right.
goes, but eventually it should be able to level. Wouldn't it?
No, it doesn't have to, because the exponential decrease from x to the third power, from 1 over x to the third power, from 1 over x to 1 over x to the third power is so much greater that when you add 1 over x to 1 plus 1 over x, when you have all those rates, small changes, they will still be big enough to notice a change in the graph. But when you add all those small changes from 1 over x to the third power, they will essentially be 0. So they will essentially.
So look at, here's 1/10, right? Here's the rate at 1/10. Where does 1 over x cubed reach 1/10? Like at around 2, right?
Yeah.
Where does 1 over t reach 1/10? Maybe out here at 9 or 10. So you're saying since it gets to 1/10 just like this one does, why doesn't it? Well, but look at how quickly it's decreasing here. So yes, the rate is 1/10 and decreasing rapidly. Here it's 1/10, but decreasing at a much slower rate. The rate is decreasing at a slower rate. Once you get to 1/10, it's not heading down as the way this one's heading down. You see? So when you get to 1/10 here, it's heading down very slowly, whereas this one heading down very quickly, much quicker when at that rate of 1/10.
Which actually allows to have a bigger accumulation.
This does.
Which is why.
Yeah, because it's hovering higher for much longer, right? And just decreasing so much more slowly, the rate.
So 2x would go even slower.
What's the rate
So
function?
the rate would be 2x would go even slower than 1 over x. 2 over x, excuse me.
2 over x.
No,
Yes.
1 over 2x.
2 over x would go.
No, 1 over 2x would decrease.
So which are you talking about? Are you talking about 2 over x or 1 over 2x?
2 over x.
2 over x, then the rate would always be double the rate would always be twice as much as what you have here. So is that going to diverge or converge?
It would go, but it would go because it's
Every rate would be twice as much as the rate is for this one if you have 2 over x. So your rate graph would be
right,
2 times as high.
right,
So that would diverge even fast. That would diverge even faster, right?
right. That's what I meant. It would increase faster.
There's
It would just be decreasing at an even
there's
slower
2 over
rate.
x. Yeah, so it's decreasing even slower. It's decreasing
Right,
half as fast, so
that's what I
you're
meant.
decreasing
Yeah, that's what I meant.
twice as much. Yeah. Okay, so what about this? We'll look at one more. So then, when you have functions like this, rate functions like this, rate is 1 over x to the p. For what values of p does the integral converge or diverge? So converge means quantity levels off. It's a finite value. Diverge is when the quantity whirls off to infinity. It's undefined. So this is quantity levels off, quantity finite, diverge, quantity infinite. So the question is, what values when for we saw Q when it was 3, it converged, right? When it was 3, the quantity converged. That was the blue one. When P was 1, it diverged. So what's the breaking point? So for what values of P will it converge?
So for p equal 1, it will diverge.
Anything bigger than 1. And we could show that. We don't have time. For P, when P is anything greater than 1, it converges. But 1, when you hit 1, that's when it doesn't go down fast enough. The rate doesn't get small fast enough for it to converge. But if you had 1 over x to the 1.001, that quantity will eventually level off when x gets really, really big. But 1 over x to the 1, the quantity will just increase indefinitely. Even though all of these rate functions are going to 0 that we're talking about, right? Okay. So we'll see you again on Monday. So check Blackboard. We'll have all the homework.